An 85.0 kilogram person is in an elevator. Determine the magnitude of the force the elevator floor is applying to the person when the elevator is accelerating down at 3 meters per second squared, accelerating up at 2.50 meters per second squared, and when the elevator is at rest. Again, in order to solve any problem, we identify all the information that's given, and drawing diagrams is a great way to identify the information. So this is what we have. We have an elevator, and there is a person in the elevator, and we have some information. We know that the mass of the person is 85.0 kilograms. We know for in part A that the acceleration is going to be 3 meters per second squared. So for part A, the acceleration is 3.00 meters per second squared. We need to make sure we identify all the forces that are acting on this person. Since the elevator is moving up and down, we definitely have vertical forces. We know that there's a force of gravity down on the person. And we know force of gravity is always equal to mg. And we also know that there is a normal force due to the elevator floor pushing up on the person. So this is the normal force. Since these forces are in different directions, one direction has to be positive and one direction has to be negative. Usually we say up is positive and down is negative. Now there's some information we can determine here. Since we know mass is 85 kilograms and acceleration of gravity is always 9.80 meters per second squared, we can determine the force of gravity acting on the person. The mass is 85.0 kilograms. The acceleration of gravity is negative 9.80 meters per second squared. It's negative because acceleration of gravity is always down. This force of gravity acting on the person is then going to be negative 833 newtons. In order to determine the acceleration that this person has, we know the net force. Since we have the acceleration and the mass, the little bell should go off in your head. We know acceleration and mass, we can get the net force. So the net force is equal to the mass times acceleration, Newton's second law. The mass is 85.0 kilograms. The acceleration is 3 meters per second squared. Now, this says down at 3 meters per second squared. Sorry, this says down at 3 meters per second squared. So this value is actually going to be a negative 3.00 meters per second squared. It's very important to make sure we have the correct signs for any vector that we're using. Acceleration is a vector. So this is going to be negative 3.00 meters per second squared. We do that calculation, and we should get a net force of negative 255 newtons. Remember, the question that we're trying to solve for is determine the magnitude of the force the elevator floor is applying to the person. The force that the elevator floor is applying to the person is this normal force. So we're trying to solve for in here is the normal force that's acting on the person. In order to do that, we now know the force of gravity acting on the person, we know the net force acting on the person, and we want to solve for that normal force. Now we use Newton's third law of motion, that the summation of force, remember the summation of force is the same thing as the net force, is equal to the normal force plus the force of gravity acting on the person, the two forces that are acting on this person. We know the net force is negative 255 newtons. The normal force is what we're trying to solve for, plus the force of gravity, which is negative 833 newtons. We solve that for the normal force, and we should get 578 newtons for the normal force acting on that person. Okay. Now let's go to part B. Part B, in this case, the elevator is accelerating up at 2.5 meters per second squared. In the first problem, the elevator was accelerating down, so that was negative 3 meters per second squared. But this one is accelerating up. Now we know that the acceleration is going to be positive 2.50 meters per second squared. And we're still trying to solve for this normal force, the force that the elevator is applying to the person. We again use Newton's second law. Net force is equal to mass times acceleration. We know the acceleration and the mass is still the same. So we go net force is equal to the mass of the object, which is again, or the person, 85.0 kilograms, and acceleration is 2.50 meters per second squared. We get a net force equivalent to 213 newtons, and that's a positive 213 newtons as opposed to the other one, which was a negative 213 newtons. we still want to solve for this normal force, so now we use the summation of forces. The net force, which is the same as the summation of forces, equal to the sum of the forces, vertical forces acting on the person in this case, which is the normal force, plus the force of gravity. The net force is 213 newtons. We want the normal force. We know the force of gravity is still negative 833 newtons. We solve that equation for normal force. We add 833 to both sides, and we should end up getting a normal force of 1,046 newtons. So in order to accelerate up, there has to be a greater force up on the person than there is down, and that's what we see. For part C, part C, if the elevator is at rest. It's a very significant piece of information if it's at rest, because if the elevator is at rest, that means the acceleration is 0 meters per second squared. We're still solving for the normal force. If the acceleration is 0, then according to Newton's second law, net force equals mass times acceleration. If acceleration is 0, then the net force is also 0. So now we have a net force of 0. We then look at Newton's third law of motion, the summation of forces. Newton's second law of motion, the summation of forces. The net force is equal to the normal force plus the force of gravity. The net force is 0 newtons. The normal force that we're solving for plus the force of gravity, negative 833 newtons. We solve that equation for the normal force. That's equivalent to 833 newtons, and that's positive. So if there's no acceleration, what that means is this force of gravity, which is 833 newtons down, the normal force up, which is positive 833 newtons, balance each other out for a net force of 0.